little earlier tonight than last time. I held you the whole time last time, and then you had to do some stuff outside. So I'll try not to do that tonight. All right, so we're going to talk about rational functions. The last part of Chapter 5 is about rational functions. Both Section 4 and 5 are both about those. So a lot of the things we cover in 4, you're going to do again in 5, and try to, put it all together as we go here. So a rational function is a function that has a polynomial on top and a polynomial on the bottom. Okay, that is a rational function. We have some function up top, it's a polynomial function, and some polynomial function on the bottom with those. All right, with a polynomial function on top and bottom, it makes finding the domain pretty standard. Okay, so if there's a x in the denominator, the thing we learned in Chapter 3 was to find the domain, you set the denominator equal to 0. So you're going to set the denominator equal to 0 to find the domain every time. This is before you do anything else. And we'll set that denominator equal to 0 and solve and find those restrictions on the domain. Most of the time, you're going to want a factor to do that. Okay, it's going to be helpful if you can factor out of that. Sometimes you don't have to factor because there's not anything to be factored there. But if it's a quadratic or anything bigger than that, you definitely want to think about factoring when you're trying to solve that, because it's going to help you when you do the next step, which would be to simplify the fraction. And again, factoring is how that's going to happen. And you're going to cancel any matching factors. Okay, so factoring, cancel any of the matching factors. So if you had an x plus 3 on the top and an x plus 3 on the bottom, you would cancel those out. What that does is it creates holes, and our particular textbook doesn't really talk about those until Section 5, but I'll go ahead and mention them here so that we are thinking about them as we go along here. It creates holes in the graph where one of those factors was canceled out, and we have to address that as we move through these things. The next thing that happens after you've simplified is when you start looking for asymptotes. And asymptotes are these imaginary boundaries, or well, they're not imaginary; they exist, but you never see them on the graph. Like if you graphed it on a calculator, you wouldn't see the asymptotes. There are vertical asymptotes, there are horizontal asymptotes, and then there are slanted asymptotes. And depending on the situation with the polynomial on top and bottom, what you have, what kind you have. So the way you want to go about this is start by finding your vertical asymptotes. Vertical asymptotes are going to come from what's left in the denominator. Okay, the simplified version of the fraction or the rational polynomial function. We're going to look at the denominator and set all those factors equal to 0, and that's going to find us vertical asymptotes, because you might have like x plus 4 and x minus 2 in the denominator. You set those equal to 0, and you get x equals -4 and x equals +2. You have vertical asymptotes at those numbers. So vertical asymptotes are going to come from the denominator of our rational function. And a lot of times your vertical asymptotes will match up with the numbers that are restrictions on your domain. The only time that they don't is if you had holes in the graph where you had factors that canceled out. And restrictions on the domain happen before you simplify. Okay, that's a very important thing that you remember, that Domain is decided before we simplify. Wholes and asymptotes are decided after we simplify. So that's maybe a star point there. Domain before we simplify. Everything else after. So vertical asymptotes usually match up. As we see examples of this, you'll see what I'm talking about. They usually match up with what your restrictions on your domain are, but they're not always perfectly one-to-one because you could have some factors that cancel out, and you won't have as many vertical asymptotes as you do restrictions on your domain. The next type of asymptote that can exist is a horizontal. Horizontal asymptotes, there's two scenarios where this could happen. The first scenario is if the degree of the numerator is less than the degree of the denominator. That's our situation. An example of that situation would be this rational function. Maybe something like x squared plus 9x minus 3 over x cubed plus 2x, something like that. Really doesn't, as long as it doesn't factor, we're okay. And the numerator doesn't factor, so that we know that there's not going to be any cancellations. So the degree of the numerator is the highest exponent on that x, so it's squared. So 2 is the degree of the top. The degree of the bottom is 3 because that's the highest exponent on the variable. So here we have a situation where the degree of the numerator is less than the degree of the denominator. If that's what's happening, you look at those degrees, doesn't really matter what else is happening, then the horizontal asymptote is at y equals 0. Okay? So degree of the numerator less than degree of the denominator. It's y equals 0. Okay? Numerator is less than the denominator. It's at y equals 0. That's the first situation for a horizontal asymptote. Situation number 2 for a horizontal asymptote is if the degrees are the same. If the degree of numerator and denominator are equal, then. Okay, so here's a situation where that might be happening. Here's a rational function, maybe something like 3x squared plus 5x minus 7 and 4x squared minus 2x plus 13. I know that neither of those trinomials will factor, so that's why I picked those. Okay. The degree of the top is 2. The degree of the bottom is 2. The horizontal asymptote will be at the ratio of the leading coefficients. So the leading coefficients are the number in front of the highest power of x. So for this one, the horizontal asymptote is at y equals a over b, and that's the coefficients degree terms. So for this one, we would have a horizontal asymptote at y equals 3/4. This one up here, it's y equals 0 because the top is smaller than the bottom. These are equal, so it's the ratio of the coefficients in front of the degree terms, also called the leading coefficients. So we would say 3/4. So there'd be a horizontal asymptote at 3/4. Okay. All right, so degree top is less, y equals 0. Top and bottom are the same. It's the ratio of the leading coefficients. Those are the two scenarios in which horizontal asymptotes can exist. Okay. When you're dealing with asymptotes, vertical asymptotes can always be there. Horizontal asymptotes, and then the next type, which is called an oblique asymptote, they never exist together. So an oblique, that's the correct word. You may hear me call it a slant asymptote. Obliques and horizontals never exist together. Okay? You're either going to have verticals and horizontals, verticals and obliques, or just verticals. It's possible to not have horizontal and not have obliques, but you will never have horizontal and oblique together. Okay? Never. Okay? The reason being that there are rules for when you have horizontal asymptotes and when you have oblique asymptotes. Oblique asymptotes only occur if the degree of the numerator is one more than the degree of the denominator. Example of that would be something like f of x is equal to x cubed plus 27 over x squared plus 5. Something like that. Here we have a degree of the numerator is 3. The degree of the denominator is 2. There is a situation in which we're going to have an oblique asymptote. So to find that oblique asymptote, it's not quite as easy as horizontal asymptotes. We've got to do long division with polynomials to do that. All right, so that would then we use long division to find the oblique asymptote. That oblique asymptote will have an equation that's of the form y equals mx plus b. It'll be a linear equation. And when we do that long division, we find out what that equation is. Okay. Again, that what I said earlier, horizontal and obliques never occur together. Horizontal and oblique asymptotes never occur together. Verticals, you're pretty much going to have those no matter what. Horizontals and obliques, you only have if these situations, these three scenarios are the only ways you're going to have horizontals. If the top is smaller than the bottom, it's y equals 0 always. If the top is equal to the bottom on degree, then it's the ratio of the leading coefficients. That's the two scenarios for horizontals. The only scenario for an oblique is the top is one more than the bottom. If there's anything else happening, then you don't have horizontals or obliques. It's possible to not have either of those. Okay, vertical asymptotes generally always exist if it's a rational function because you've got an x in the denominator. It's there. Okay, so it can happen. So we got to look through that. So let's look at some examples and try to pick up all of these things and try to work our way through a rational function and pick up any of those things that exist. Again, not all of them are going to be there for every problem, so we've got to follow our rules for when those exist. So let's call this example A. Here's f of x equals x squared plus 7x plus 12 over 4x squared minus 1. So here are the things we're going to find. We're going to find the domain. And I go ahead and do vertical asymptotes, and I'll abbreviate VA for vertical asymptotes, horizontal asymptotes, and oblique asymptotes. Those are the four things that we're going to look for first, and then we'll start adding in the other stuff from the fifth section 5 after we've kind of mastered this part. Okay, so the first thing that we should do is find the domain. Before we simplify anything, we're always going to try to simplify it. It's a fraction, so you know anytime you're dealing with fractions, you always try to simplify if possible. So, but before you can simplify, you need to find your domain first. Okay. So to find that domain, we're going to set 4x squared minus 1 equal to 0. So again, when you're trying to find the domain, it is usually helpful to try to solve that by factoring if possible, because it's going to help you when you go to simplify. Okay, so that one, how does 4x squared minus 1, how's that going to factor? We think about quadratics and how things work with those. I'm thinking, okay, well, it's a squared piece minus another square number. So I'm thinking that's a difference of squares. So what squared is 4x squared to be 2x. What squared is 1 to be 1. And then to multiply by negative 1, you got to have a positive 1 and a negative 1. So there's the factors for the denominator. Okay. And then I'd set each of those equal to 0 and solve them. And there's negative 1/2. And then 2x minus 1 equals 0 would be positive 1/2. So our domain x does not equal plus or minus 1/2. Now, what I want to do now is go to back to the problem and look at possibly factoring the numerator if it will. There's no rule or law that says it has to, but this one will, but I don't know if anything's going to cancel. So if I try to factor that quadratic there, and it's something that multiplies to be 12 and has to be 7, 4 and 3, right? So it's x plus 4 and x plus 3. So I factored the numerator and the denominator to try and see if I could simplify. I did all that work and nothing is the same. I don't have a same factor on top and bottom, so nothing's going to cancel here. So what that tells me is that I don't have any holes in this graph, and that's kind of alluding to section 5 that we'll talk about in a minute. There's no holes because I didn't cancel out any factors. Okay? And that also tells me that my vertical asymptotes are just going to come from those two factors that are on the bottom. Yes, ma'am. Multiplying to be 12, adding to be 7. 4 times 3 multiplies to be 12, and 4 plus 3 adds to be 7. So I use that an X thing just to organize my thoughts on factoring. Guess and check is how I learned it, but that's not necessarily how I teach it now. But it's all a different version of guess and check now to do it. But it's all right. So now we've got everything factored. Nothing simplifies. So when we think about our asymptotes, we're just going to refer back to the original. If something simplifies, then I've got to look at some things differently. But because nothing simplifies, I'm going to go back to the original when I look at that. I know my vertical asymptotes, because nothing canceled out, I'm going to have a vertical asymptote at x equals positive 1/2 and another one at x equals negative 1/2. I've got two of them because I have two factors in the denominator that didn't cancel out. And when I set them equal to 0, it solves out to be positive 1/2 and negative 1/2. Those are the same values from my restrictions on my domain. Remember, those tend to match up most of the time. Not always, but you won't ever have a vertical asymptote that isn't a restriction on the domain. Okay? To be a vertical asymptote, it had to be in the restrictions on the domain somewhere. Okay? It is possible to have a restriction on the domain that is not a vertical asymptote, though, because some stuff could cancel out. All right. Now, we've got to decide about horizontal or oblique, because it's one or the other. It's never both. Okay, so we look at the degree of the original problem. The top has a degree of what? 2, and the bottom has a degree of 2. So they're equal. Which type of asymptote occurs when they're equal? A horizontal asymptote. And what's the shortcut to doing that? The coefficient. So the coefficient of the numerator is, leading coefficient of the numerator is 1. Leading coefficient of the denominator is 4. So we have a horizontal asymptote at y equals 1/4. Because we have a horizontal asymptote, we have no oblique asymptotes. Remember, they will never occur together. If we were to graph this, and I want to show it to you so that we have looked at some graphs here, because that's what we're finding all this information to describe things that are happening on our graph. Parentheses divided by parentheses 4x squared minus 1. So I'm just typing in, I'm being careful to put the numerator in parentheses and the denominator in parentheses. The beautiful thing about this is if you put the original problem in or the simplified one, it's the same. Okay, the graph should look exactly the same. Okay, so I'm just using the original and I'm hitting graph, and we see what's going on here. So we've got a vertical asymptote at 1/2 and at negative 1/2, and then we have a horizontal asymptote at 1/4. Okay, so right here, negative 1/2, there's a vertical asymptote. Here at positive 1/2, there's a vertical asymptote. We see how this graph kind of bends and starts getting vertical right there. That's what's happening at that vertical asymptote on both sides. The horizontal asymptote at y equals 1/4 is right here. What do we notice about this graph? Is it crossing the horizontal asymptote? It does. Okay, for this one, it does cross that. You can cross horizontal and oblique asymptotes, but you never cross vertical asymptotes. Those are the things that's one of the things you would need to know at some point is, does it cross the asymptote? Well, you can look at the graph and tell if it does. And we'll work on finding where it crosses here in just a little while, okay? So just getting that idea in your head as we start building up to doing that stuff. Look at another one. Here's our function, g of x. Let's do x squared plus 7x plus 10 over x cubed minus 25x. And again, we're going to find those things. We're going to find the domain, the vertical asymptotes, horizontal asymptotes, and the oblique asymptotes, if they exist. We know domain and vertical asymptotes are going to exist. Okay. So to get the domain, what do? Set the denominator equal to 0. So that's what I'm going to do. I'm going to go down here. X cubed minus 25x equals 0. And I'm going to do my best to factor that because I know it's going to help me later on when I go to simplify. So x comes out as a greatest common factor between those two pieces. And that would leave me x squared minus 25. And I know x squared minus 25 factors as what? Good job. So I get those three factors. So when I go up here to do my simplifying, I know I'm going to have that. Set all those equal to 0. So I get x equals 0, x equals -5, x equals +5. So my domain is all x's as long as x does not equal these three numbers, 0 and plus or minus 5. That's usually how I'll write that. So we found three numbers that were restrictions on our domains, 0, -5, and +5. Now we need to go and try to simplify our rational function. So we need to factor the numerator now. So we need something that multiplies to be 10 and adds to be 7. So 5 and 2, good. So I have x plus 5 and x plus 2. When I go to simplify that, what cancels out? What's the matching factor on top and bottom? Those x plus 5s, they cancel each other out. So my simplified version has x plus 2 over x parentheses x minus 5. Okay, move my horizontal asymptote sign down a little bit. You may find it helpful to multiply that back out so that you can see the degree a little bit better. It's not necessary to find the degree, but it is sometimes helpful to just distribute that x back out so that you see the denominator has a degree of 2 and the numerator has a degree of 1. Okay. So next step is vertical asymptotes. Vertical asymptotes come from where? No, that's horizontals. What are our verticals? The simplified denominator equal to 0. So we've already set the denominator from the original problem equal to 0. Well, when we simplified, we got rid of one of those pieces. Got rid of the x plus 5. Okay, so we've only got x and x minus 5 left. So the horizontal asymptotes we have are x equals 0. Horizontal. Vertical asymptotes we have are at x equals 0 and x equals 5. We had two vertical asymptotes, but we had how many restrictions on the domain? How many numbers were there in the domain that were out of it? 3 of them. Normally they match. Notice we got 0 and 5. Well, 0 and +5 were in the domain restrictions, but we don't have everything that's in the domain restriction on this one. This is one of those where we lost part of the domain restriction when we went to do vertical asymptotes. So we only have vertical asymptotes at 0 and +5. Now we got to decide, is it oblique asymptote or horizontal asymptote? So we look at the degree, looking at my simplified version. So degree of the top is what? 1. Degree of the bottom is 2. So 1 is less than 2, right? So the top is smaller than the bottom. Which one does that tell us we have? We've got a horizontal where? At y equals 0. No work involved in finding that. It's a horizontal asymptote at y equals 0, which means what do we do with the obliques? There's not any. Because remember, you cannot have horizontal asymptotes and oblique asymptotes at the same time. Okay.
So how'd you get the y equals 0?
Because the degree of the top is smaller than the degree of the bottom, it is automatically y equals 0. It's a rule.
So even if it's flat.
One of them's x cubed, and as long as the top is smaller than the bottom, it doesn't matter by how much. If the top is smaller than the bottom, then it's automatically at y equals 0. The reason that it's doing that is because a rational function is really division of two functions. If you got, it's kind of like trying to divide 9 into 7. How many times will 9 go into 7? It won't, will it? 0 times. The same way with polynomial functions or rational functions. If I took a squared and try to divide it into a plain x, it won't go. Where if I took a squared and tried to divide it into x cubed, squared does go into cubed, right? So if the top is smaller, it's kind of like dividing 7 by 9. 7 can't be divided by 9 because the 9's too big. Same way here, x squared plus 5 or minus 5x, the denominator is too big to go into x plus 2 on the top. And so that's why it's y equals 0 there, is because it can't go into it at all. All right. When they're equal, when you divide it, if you actually did the division with the polynomial, then it would go into it exactly that ratio of the leading coefficients would be how many times it goes into it, which is an interesting thing. All right, let's look at another one and see if we can discover something else happening here. Example C. F of x equals, let's do 8x squared plus 26x minus 7 over 16x squared minus 1. Take that back. Let's not do that one. Back up. Let's do x cubed, x squared, x. There we go. Now, all right. Again, we're going to find the same things. We're going to go domain, vertical asymptotes, horizontal asymptotes, oblique asymptotes, if either of those exist. Okay. So let's get the domain. How do we do that? Denominator equal to 0. So we got 4x plus 1, 4x minus 1, because that's the difference of squares. And then set those equal to 0. What I want you to understand here is I'm using factoring to solve every one of these, but that's not the only way. If you're having trouble finding them, the factoring you got to get better at. It's just you got to. But if you're just needing to find the restrictions on the domain, don't forget you've got quadratic formula that you can use to help you get those. If the question only asks for restrictions on the domain and you're faster at doing quadratic formula than you are factoring, factoring is not the only way to solve 16x squared minus 1. You can do other things. You can solve that one by square roots or whatever method, or a quadratic formula works fine too. So, but factoring is the most helpful method if you're going to go and do all this other stuff for that rational function. Okay, so we get two answers: negative 1/4 and positive 1/4. Right. So restrictions on the domain. All x's as long as x isn't plus or minus 1/4. Yeehaw. Now let's look at the factored form of the numerator and denominator. So we got 4x plus 1, 4x minus 1. The numerator, 8x cubed, 26x squared, and negative 7x all have an x in common. So I pull an x out. And I think I can go a little further there and get 8x squared plus 26x plus or minus 7. That'd be multiplying to be negative 56 and adding to be positive 26. Just thinking about that factoring there. What things multiply to be negative 56? 8 and 7. But obviously that's not right. They're not far enough apart. So we need something bigger. 56 and 1 is definitely bigger, but it's too far apart. So we need somewhere in between. I know 56 is an even number, so I'm going to try 2 times what gives me 56? 28. But I need it to add to be a positive 26 and multiply to be negative 56, so I need the 2 to be negative. Okay. So to factor that, maybe I got to do a little scratch work somewhere. I got 8x squared. Originally, it's plus 26x minus 7. Now I'm going to put it in there as plus 28x minus 2x minus 7. And group. Those two have an 8x in common. And that's going to leave me x plus 7. Excuse me, 2x plus 7 is 8. 8 doesn't go into 28, does it? 4 does. Let's do it that way. Because that's the right number. What? 4 goes into 8 and 4 goes into 28. 4x times 2x plus 7. All right? And then the second group, they're both negative, but they don't have anything else in common other than that. So I'm going to pull out a negative 1 so that it'll change the sign and those parentheses will match. So if they don't have anything else in common, you at least pull out a 1. If they're both negative, you're going to want to pull out a negative 1. And that leaves us the factored form of 4x minus 1 and 2x plus 7 for that quadratic piece on the top. So I've got x parentheses 4x minus 1 and 2x plus 7. So there's the factored form of our polynomial on the top and the factored form of our polynomial on the bottom. The 4x minus 1s cancel each other out. So that I've got x 2x plus 7 over 4x plus 1. What's the degree of the top? 2. I think it'd be helpful if we went ahead and multiplied this back out. 2x squared plus 7x over 4x plus 1. That I think is going to help us when we go to our asymptotes for that. Because we canceled out 4x minus 1, that means we only have one piece in our vertical asymptotes, and that's that x is equal to negative 1/4. That's the only vertical asymptote I have. I lose the positive 1/4 from the 4x minus 1. So I'm looking at the simplified version, which is right here. That's the part I'm looking at to get that vertical asymptote. 4x plus 1 gets me that. The degree of the numerator, we've already said, is 2. The degree of the denominator is 1. So that means the top is how much more than the bottom? 1 more. So that means we have what kind of asymptote? Oblique. So we don't have any horizontal asymptotes. We have an oblique asymptote. And this one takes long division to get there. So we're going to do long division of that simplified version. So we got 4x plus 1. And we're dividing that into 2x squared plus 7x, and I'm going to put a plus 0 on the end because I think I'll need it because there's nothing out there. So I'm going to try to get there. Now, this one's a little tricky because you're trying to divide a 4x into a 2x squared. So the way you want to think about polynomial long division is you want to think, okay, what times this first piece gets me this piece? So what times 4 would get me a 2 in front? A negative would just give me a negative in front. What times 4 is 2? And sometimes it can be helpful to set yourself up a little problem. 4 times something is equal to 2. And solve that equation. What's 2 over 4? It's half. Oh. Half of 4 is 2, right? So 1/2 times 4. Now, what times x would get me x squared? Another x. So I need a 1/2 x to get this. So I'm going to say 1/2 x up there. 1/2 x. And then I distribute that 1/2 x to everybody on the front. So 1/2 x times 4x is the 2x squared that I wanted. 1/2 x times 1 would be 1/2 x. Parentheses, subtract. Because this one has fractions in it. It's a little tougher, but it's doable. I think it's good to have that fraction in there because you get to see what's happening. It makes you think a little bit more. All right, so the 2x squareds are going to cancel out. And then we got 7 minus 1/2. 7 minus 1/2 would be 6 1/2, right? So 6.5 or 6 1/2 would be 12. 13 over 2 would be the fraction form of that. So this is where setting up that little problem is helpful. What times 4 will get me 13 over 2? That's the tough one. So I've got somewhere I'm thinking 4 times n is equal to 13 over 2. And to do that, I'm going to divide by 4, which dividing by 4 mathematically is like multiplying by its reciprocal, which is 1/4. That'll be 13 over 8. Remember, an oblique asymptote is going to be what kind of equation? Oblique asymptotes, go back up here to the explanation. Oblique asymptotes are going to be slope-intercept form. When I go back down here to C, there it is. Right there, mx plus b. That's slope-intercept form. I don't even have to do the multiplication and the subtraction. I don't have to do anything else. If I can get that number there, I'm good. That's my slope-intercept form. That's my oblique asymptote, is that y equals 1/2 x plus 13 over 8. I want to show you this one on the graph so you can see that oblique asymptote happening. I'm going to try to remember the original is 8x cubed plus 26x squared minus 7x over 16x squared minus 1. Okay, so parentheses 8x to the third plus 26x squared minus 7x parentheses divided by parentheses 16x squared minus 1. Graph. I can tell that one has an oblique asymptote from its graph. You see it getting slanted there? That tells you if I graphed my oblique asymptote that I found, 1/2 x plus 13 over 8. Look at it go right through that spot. I know I found the right one when I do that. That's a checking place there. We also know we have a vertical asymptote, at y equals, or I mean, excuse me, x equals -1/4. That's right, about right there. You can see those two lines getting vertical, approaching the asymptote. What's happening for that? Okay. So we see that the horizontal, or we don't have a horizontal one here, we just have the vertical and the obliques. We never have horizontal and obliques together. When you look at the original graph, you can always tell if you've got an oblique because it'll have something that runs a slant like that. Okay. All right, let's look at section 5 and kind of add some things to it and see what we can do with that. So it's the same, all of the same idea. I'm not even going to change to another set of notes here. So this is picking up 5.5. We're picking up the extra stuff that's involved. Again, we're going to find the domain. We're going to simplify, and then we're going to get asymptotes, and we're also going to find intercepts, holes in the graph, and if it crosses the asymptote is what we're going to do for 5.5. So let's look at an example and try to do those things. Okay, so f of x is equal to x squared minus 4 and over x squared plus 5x minus 14. Just by looking at the original, what do you know this one has as far as asymptotes go? It's got a horizontal. Why do we know it has horizontals? The degrees are equal. Even on the unsimplified version, you're going to be able to tell that right off the bat. Look at the degrees. They're the same. So I know that I'm going to have horizontal asymptotes, which means I will not have what? I will not have obliques. Okay. So I could go ahead and put that in there as none. Okay. All right, so let's find the domain. X squared plus 5x minus 14 equals 0. Again, I'm going to use factoring, but that's not the only way to find your restrictions on your domain. Remember, you have quadratic formula that you can use. You have solving by completing the square or graph even could help you here. But factoring is going to be helpful for later on. So that's why I'm going to factor it. So we need something that multiplies to be -14 and adds to be +5. Seven and -2. So +7, -2. So x plus 7 and x minus 2 are my factors. So that means my domain restrictions are going to be x equals -7 and +2. So x cannot equal -7 or +2. There's my domain. Factored form of the denominator up there to get the factored form of the numerator. What are the factors for the numerator? Yeah, so x plus 2, x minus 2. That's beautiful because what cancels? X minus 2. Leaving us x plus 2 over x plus 7. What's our only vertical asymptote? Which part of the denominator canceled out? The x plus 7 or the x minus 2? So that means this is our only vertical asymptote. Is at -7. Because that canceled right there, what that does is it creates a hole at 2. Okay. Because 2 is still a restriction on the domain. That means x can't be 2. So there's a hole in the graph. It's an empty circle. Like when you won't see it when you graph it with the calculator, but if you were graphing it on paper, you would see that line kind of running wherever it's going. And then we got to x equals 2, there'd be an empty circle there. And then it would just pick up and keep going from there. So instead of having a vertical asymptote at 2, we've got a hole at 2, which is an empty circle when we go to do that. So we're going to address that in just a second. All right, so y'all have already told me there's a horizontal asymptote. Where is that horizontal asymptote? What's the degree of the top? They're equal, right? So it'd be 1 over 1, right? Which is 1. We'll reduce it. So y equals 1. We have a vertical asymptote at -7, a horizontal asymptote at y equals 1, because we're looking at the leading coefficients, 1 over 1, and no oblique asymptotes. Okay. Go down here. We're going to talk about that hole at x equals 2. Okay. What we want to do is find f of 2 in our simplified version. So that means put a 2 in for x. Because we need to know the ordered pair for that hole, where that empty circle is going to be. So 2 over 2 is 4. 2 plus 7 is 9. So a hole at x equals 2 creates an empty circle at the ordered pair 2, 4 over 9. We know that's where we have a hole in our graph at 2, 4 over 9. The y value is 4 over 9. You find that by plugging that x value into your simplified version to get that ordered pair for the hole. Okay. Let's find intercepts. What kind of intercepts do we find when we're talking about functions? X and Y intercepts, okay? So if we're going to find X-intercepts, how do we find X-intercepts? How do we find X-intercepts of any type of function? Set the function equal to what? So we're going to take x plus 2 over x plus 7 and set it equal to 0. The beautiful thing about rational functions is the only part you have to worry about, the only way that fraction could equal 0 would be if the top part's equal to 0. Remember, 0 divided by anything is 0. So all we got to do really is set the numerator equal to 0. X plus 2 equals 0. That would be x equals -2. So we have an x-intercept at -2, 0. X-intercepts is where the numerator is equal to 0. Okay? And you want to use your simplified version. Okay? Don't use the original. Use the simplified version. Okay? Now, got to find y-intercepts. For any function, how do you find the y-intercept? Yeah, what value of x on a y-intercept? What's the value of x on every y-intercept that ever existed? 0. So we're going to plug a 0 in for x. 2 plus 0 is 2. 0 plus 7, 7. So it's at 2/7. So we have the x-intercept at -2, 0, and a y-intercept at 0, 2 over 7. Okay. We found out a lot of stuff about this one. There's one more thing we want to do. We want to decide, does f of x cross that horizontal asymptote? Okay. So this is the last question for this problem. Does f of x cross y equals 1. We're going to check our horizontal asymptote or our oblique, whichever one we have. Okay, remember we will only have, if we don't have a horizontal and we don't have an oblique, then you don't have to worry about it crossing, okay? Because it's never going to cross verticals. It's only going to cross horizontals or obliques. So does f of x cross y equals 1? So what you want to do is algebraically set your simplified version, 7 on the bottom, equal to 1. Because that's the horizontal, whatever that asymptote is. If it's a horizontal asymptote, it's just going to be equal to a number. If it's an oblique asymptote, it's going to be equal to some linear thing like mx plus b over here. We'll look at an example maybe that does that in just a little bit. Okay? We're going to solve this. This is a little bit more difficult to solve, but it's not too bad because this is division over here. So to undo that, I'm going to multiply by x plus 7. And because that y equals 1 is the oblique or the horizontal asymptote, just multiply x plus 7 times 1. And if I go to solve that and I subtract x, what happens to the x's? They disappear. Does 2 ever equal 7? Never, ever will 2 equal 7. Okay? So this is false. So does it cross y equals 1? No. If you got an answer that x equals some number, then that's where it's going to cross. Okay? If you get this and the x's cancel out, it doesn't cross it. Okay? Another way to decide that would be to graph the thing and look at that horizontal asymptote and see if it crossed it like this. So if we took y equals, clear out these things, and let's go to our, the simplified is shorter to type in, so that's what I'm going to use. X plus 2 divided by x plus 7. I've got a horizontal asymptote at y equals 1. I've got some vertical asymptotes. We're not worried about those. We're only worried about whether it crosses that one. As we see, there's the one across the middle there. That's my horizontal asymptote. It looks like it's getting up there to it. If I hit trace and typed in something like 30, it won't fit it on the screen. I have to zoom out. So let's zoom out. Number 3. Flitter. Zoom out. Notice it's hard to tell the screen colors sync still. So as it's getting closer and closer to it, but if you moved out here and really zoomed in there, you can see there's a little gap between it. It'll be real obvious if it crosses it. And it usually does it pretty close to the center of the graph if it does cross it. Algebraically is the real way you want to check it, but you can check the graph and get an idea whether or not you need to even do all that algebra. Okay. Hit zoom so it can get back to my normal view. All right, let's do another. New page. All right, example B. F of x is equal to 6x squared plus 9x over, let's do 3x minus 2. This works out pretty nice. Pretty cool looking. Just looking at the original, what do we know about the degrees? The degree of the top is 1 more than the degree of the bottom. That tells us we're going to have what? An oblique, which means we're going to have to do some long division, which is okay because we need to practice and we need to see that. So let's find the domain first. So before we do anything else, we're going to take that denominator, set it equal to 0, and there's no factoring that can be done on this one, which is beautiful. So you just add 2, 3x equals 2, x 2/3. So our domain, our restriction on the domain is x cannot equal 2/3. That's what we know about our domain. I know the bottom part didn't factor. Does the top part factor in? Well, do 6x squared and 9x, do they have anything in common? 3. And they both have an x. So I could pull out a 3x, and that would leave me 2x plus 3 in the parentheses. Okay? So we factored both the numerator and the denominator as much as possible, and we notice that nothing cancels here. 3x minus 2 doesn't match plain 3x. 3x minus 2 on the bottom does not match 2x plus 3. So nothing is going to cancel. So that means that because nothing canceled, my domain, x cannot be 2/3, is also my vertical asymptote. It's the same number. X equals 2/3. I don't have to do any extra work there as far as thinking about, oh, this canceled, so I drop it out and keep the only one. The only one I've got is 3x minus 2, and it's my vertical asymptote. Okay. What do we know about horizontal asymptote? It doesn't have any. That's good. We can go straight to oblique asymptote. So to get that oblique, we got to do that nasty long division. So we're taking 3x minus 2 into 6x squared plus 9x, and I'm going to put a plus 0 on the end because I figure I'll need it to get to that slope-intercept form. This one's a little better starting off because we're looking at 3x. What times 3x will give me 6x squared? 2x. Good job. 2x up here. And then I take that 2x and distribute. 2x times 3x is 6x squared. 2x times negative 2 is negative 4x. Parentheses and subtract. The x squareds cancel. That's what I wanted to happen. And then I end up with 9x minus negative 4x. What is 9x minus negative 4x? 13. Okay, it started out nice. Now 3 times what gives me 13? 3 times what gives me 13? Divide by 3. Oh, it's just 13 over 3. That's nice. I don't even have to do the multiplication and stuff to get there because this is my oblique asymptote. Y equals 2x plus 13 over 3. That's my oblique. Okay. All right. Well, the next thing we did on example, I wrote B there, but it was example D, I believe. It's the one we were on before, was look at the holes. Well, are there any holes for this graph? And how do I know that there are not? It didn't simplify, so there are no holes. That's how I know. If there's a factor that cancels, there's a hole in the graph. If there's not a factor that cancels, there's no hole. So no holes. No holes. So we need to go to intercepts then. We can do X intercepts and Y intercepts. X-intercepts are usually the toughest. What do we do to find an X-intercept? What equal to 0? All right, good. The simplified version. So I got 6x squared plus 9x over 3x minus 2 equals 0. And if I wanted to, I could go ahead and start with that factored form. Either of those. I went back to the original because it didn't simplify at all, but I really probably should have went to the factored form because that's going to save me a step later on. What happens to the 3x minus 2 on the bottom? I multiply by it, but 0 times 3x minus 2 just goes away. And I end up with 3x parentheses 2x plus 3. That's the factored form of the numerator equal to 0. Remember, really, for x-intercepts, all you're really doing is setting the numerator equal to 0. So I set each of those factors equal to 0. Divide by 3. X is equal to 0. Subtract 3. 2x equals negative 3. Divide by 2. Negative 3 over 2. I have two x-intercepts. I have an x-intercept at 0, 0, and at negative 3 over 2, 0. Two x-intercepts for this graph. For the y-intercept, what do I do with 0? Put it in for x. And that makes this one easy peasy. That's 0 on the top. 3 times 0, 0 minus 2 is next. Well, that's just 0. It doesn't matter. Notice that this y-intercept and this x-intercept are the same. That's the only time they will be, is if it's at the origin. If the x-intercept is at the origin or the y-intercept is at the origin, they match up. Okay? The next question would be, does the graph cross the oblique asymptote that we found? Okay? Does it cross the oblique asymptote? How do we decide? Yeah, we set the, that's not over 2, it's over 3. Set the function equal to that oblique asymptote. So we're going to set 6x squared plus 9x over 3x minus 2 equal to 2x plus 13 over 3. This one's a little tougher. A lot of the work is the same. Three x minus 2 on both sides. And then I'm going to have to multiply this out with distributed property a couple of times. So 2x times 3x, 6x squared, 2x times negative 2 is negative 4x. 13 over 3 times 3 is 13x. 13 over 3 times negative 2 would be negative 26 over 3. So a nice ugly number there. But it simplifies out. We got 6x squared plus 9x equals 6x squared plus 9x minus 26 over 3. What happens to the 6x squareds on each side? And the 9x's on each side? They're going to cancel out. When you go to do that subtraction, they're going to cancel each other out. And so all of the x's are gone. And you got 0 equals negative 26 over 3. Does that ever happen? Never. So that's false. So does it cross it? No. All right. Let's do one more. We'll be out of here. Last one of the day. Well, this is a lot of stuff, but you're doing the same thing on every one of them, so it makes it seem like a good process. All right, so f of x, 3x squared minus 9x over x squared plus x minus 12. All right. Domain. How do we get that? Denominator equal to 0. So x squared plus x minus 12 equals 0. Factor that. Oh, yeah. Too far apart. Got to add to multiply to be negative 12 and add to be a 1 because there's a 1 in front of that x. 6 and 2. Yeah, it's 3 and 4. Yeah. Positive 4, negative 3. Negative 4 and positive 3 would still get me multiplying to be negative 12, but it wouldn't add to be positive. So it's a positive. So the domain then, x can't be negative 4 or positive 3. So there's the factored form of the denominator. How can we factor the numerator? Good job. 3x leaves x minus 3. Well, that's handy because what cancels? X minus 3 is canceled. So that means our vertical asymptote, what's the only vertical asymptote I have? The negative 4. Good. So I've got a simplified version of 3x over x plus 4. Looking at the degrees, what do I know about horizontals and obliques? Excuse me, sorry. That's right. So we don't have an oblique. What is the horizontal one since the degrees are equal? So the coefficient of the top is 3. The coefficient of the bottom is 1. So 3 over 1 y equals 3. And we don't have an oblique. Do we have a hole? Where? At x equals 3. We need to find the y value that goes with that. How do we find the y value that goes with an x value? Plug it in. Yeah, 3 plus 3 over 3 plus 4. 9 over 7. So we know if we went to that ordered pair on the graph, that'd just be an empty circle there. What we know about that. Intercepts. Get the X-intercept first. What's the shortcut for getting X-intercepts? What part of the problem do you set equal to 0? Just the numerator. And this one's really easy because you just got 3x. 5 by 3. X is 0. So we have a X-intercept at 0, 0. Which tells us we also have a Y-intercept at, plug a 0 in for X. And we get 0 over 4, which is 0, 0. The same for the X and Y intercept here, just one. Now that because it's the origin, and that's the only time that can be that. All right. Last thing would be deciding if it crosses that horizontal asymptote. So to decide that, we're going to set 3x over x plus 4 equal to 3. Multiply by x plus 4, the denominator. 3x equals 3x plus 12. And we see a familiar thing happening. 0 equals 12. That doesn't happen. So this does not cross. All right, problems that you could look at this week. Page 380, 15 through 55. That would get you, just the odd ones there. There's plenty. Get you going there. And then, of course, you'll have the Canvas quiz that'll be due that Monday night after fall break. We'll have our test that Monday evening after fall break. I will send you a review for the test this week. That way you've got it for 2 weeks there to get ready for it, and you can email me questions about that, if you're working on that and being ready for it. So got you out of here.